It's they take it is an averaging, I believe at least, and they just train models, and they add it to the ensemble, and if it boosts the ensemble performance slightly, then they just keep it. But yeah, I think it is just an averaging of the output. So another important point is that there's a lot of tricks to actually getting your data ready for a deep neural network, and one of the tricks is that you use data augmentation, whereby you increase the number of samples effectively that you have to train with by doing a bunch of transformations on the input. So we talked about priors earlier, and so here you're applying some priors to your data. And you're saying, okay, I know that if this data example is of this class, then if I rotate it slightly, it should still be of that class. So you're just incorporating some more priors. So if you have your image of Yisong, you can crop it to a bunch of different crops, flip it, and rotate it. It's still Yisong. And so another important question you might have is, what actually are these models learning? So at the first layer, these filters are actually operating on the image space. They're working in RGB images. So you can actually go in and just directly visualize what the filter is, just visualize it as an image. And what do you see here? You see a bunch of striped patterns, a bunch of gradients, and different combinations of colors, and a few checkerboard kind of looking things. But yeah, for the most part, kind of what you would expect, sort of similar to what you see with neurons in the primary visual cortex, where now they're extracting this kind of basic pattern, like just a bar in a particular orientation, or a particular combination of colors, for instance. Now, once you get beyond the first layer, you actually can't visualize these filters directly. You have to do a few tricks. So one thing you could think of doing would be, I'm going to feed my images into the network, and whenever I see this filter light up maximally, I'm going to keep that image, and I'm going to just say this image pretty much describes that filter. So that's one approach. Another approach would be actually reverse the convolutional operation and do what's called a deconvolution. Now, these convolutional neural networks are actually they're not invertible. So you can't directly invert the transformation that's being done, but you still, if you take the representation of an image at a particular layer and use a deconvolution operation to pass it back through the network, then you can get somewhat of an idea of what that filter is actually selecting for. And another approach would be, I'm going to treat it as an optimization problem. I'm going to have an input, and I'm going to have a filter. And what I'm going to do is backpropagate from the filter to the image to try to actually increase this filter's activation. So I'm going to try to change my image in such a way that this filter lights up even more. It's more active. And this works somewhat, but you have to be a little careful with it, because it can give some weird results. So these visualizations are actually done using deconvolution. So these are the maximal images, and then the other visualizations that I'll show you are deconvolution. So this is at layer 2. And what do you see at this layer? You see, well, I can definitely see some different color blobs. So you see there's a filter that's specifically selecting for red over in the left corner there. You have a lot of different orientations of lines. You have some circular patterns. So you have like these circular patterns here. You have like a cheetah skin like pattern here. Very fine textures here and here. But yeah, a lot of either very basic shapes or textures or lines of things of that nature. And when you visualize the deconvolution of these images, you see that, yes, indeed, these filters are they're highlighting these specific features. They're highlighting the lines, they're highlighting the shapes, the circles. And so when you go to the next layer, what you see are actually these images are getting slightly more complicated. So now you're starting to see, like in the top, up here you're seeing images or filters that are selecting, it seems like for some type of combination of features that looks like a face. You're seeing things like round fruits almost, and heads of birds. You're seeing some more specificity that's being performed here. And again, you see it is highlighting those particular features. Like you have, like this is a jack-o'-lantern feature almost that's highlighting fire, so that appears to be looking for fire specifically. And then at the next layer, you now see a lot of faces of dogs. So ImageNet has quite a few dog classes in it. There's a Stanford Dogs data set that's a subset of ImageNet. And you see, again, a lot of shapes. You're seeing over on the left there some butterflies and spokes of wheels and things like that, a lot of flowers. So again, more shapes and dog faces. And similar story once you get to layer 5, you're seeing even more complicated features that are being selected out of these inputs. So I've talked a lot about object recognition, but that's obviously not the only thing that we do with vision. We, for instance, detect objects. We know where they are. We don't just know what they are, we know where they are. I told you about how we have these two streams in the human visual system. And so there's been some approaches to tackling this locating an object. It seems kind of almost counterintuitive to think of these as separate things, but truly they are. Knowing what something is versus where it is, those are different things, but they are related. So what the approach has been for a while was basically just take a bunch of crops out of the image and then classify those crops and then put it through a linear classifier of saying, is this object, yes or no? Is this object, yes or no? And in that way, it's kind of a brute force approach to it. It's incredibly slow, but it works. So this was called RCNN. Came out a few years ago. And you can see that now you can detect ladybug. So you know exactly where the ladybug is located in the image. You know where this bird is, where there's a cat wearing bunny ears. You can select out these specific things. But a more recent approach to this is actually use the neural network itself to generate a proposal for where to look for an image. So this is perhaps getting closer to what the human brain could be doing, where you're not just looking all over the place and saying, okay, over there it looks more like a water bottle, for instance. You have some notion of where to look. So these networks are giving you region proposals, which are then being classified. And yeah, it's interesting work that's being done and dramatically improving the speed at which you can detect objects. So it's almost to the point of real-time object detection. Very cool. And another kind of cool thing that people are doing is actually segmenting objects. Instead of just saying, there's a bounding box around an object, you're saying, this set of pixels belongs to this object. So how would you actually do that? Because it's kind of, if you think about what we've been doing, you're decreasing the spatial resolution, so you're losing the spatial information as you go up the network. How do you get back to knowing where an object is located and specifically what pixels belong to it? So on the other hand, if you don't know what you're looking at, how can you say which pixels should be together necessarily? So you have to combine this high level, what is there, with this low level, here's where it is. So what they actually do is they feed the image up through the network and then they have a downward feedback stream that's generating an output map of the segmentation. So you have inputs from the very top that are telling you what is there, that are actually dictating how you should form the maps at the lower layers. So you're using this high-level information as well as low-level information, which is kind of a cool approach. Another cool thing that people are doing is key point estimation. So if you look at a human, for instance, you can identify certain key points and define a skeleton for the shape of a human. And so you can then reason about, well, this human is doing a tennis swing, this is how the body is configured, which is information that you wouldn't necessarily get out of a standard convolutional network. So there's some interesting work being done here as well. So I just wanted to touch on some applications briefly of, this is very cool, obviously we can recognize objects, we can locate them, tell where they are in images, but what practical applications could you foresee using this for? So the kind of original use case for these convolutional neural networks was, I told you, in reading checks at ATMs, reading the amount that's written. But you can also think of automatic kind of transcribing your handwritten notes into text. If you've ever seen this tool, it's really quite fun. It's called the Detectify, where you draw a LaTeX symbol, and it tells you, it recognizes that symbol and it tells you what the most similar symbols would be in LaTeX code, which is helpful in that we don't have to look up every single thing. Obviously, self-driving cars are huge, so we might think of using these for pedestrian detection. And actually, most self-driving car approaches don't really make a lot of use of convolutional neural networks. They don't really use this visual information. It's primarily LiDAR. But there are some companies that are starting to use more vision-based approaches as kind of a fail-safe in case the LiDAR doesn't work. Another thing is face detection and recognition. So to know who's working at my laptop, to know if I want to put a funny filter on my face and send it to my friend. You could, for instance, do convolutional neural network on that. And finally, there's also, you can search by image. So this is a more recent introduction, but you can search for products on Amazon using just images. You can also take a product on Amazon and see how it would look. Like if you wanted a TV, you could see how it would look in your house. So you calibrate it with like $1, and then you project the TV onto where you would want it, so you can see things like that. And I wanted to touch on one application that's near and dear to me, because we work on birds in the Vision Lab, which I'm a member of. And so this is part of fine-grained visual categorization. Your task is to, instead of looking at a bunch of different objects, you're looking at objects that are all very similar. So in this case, for instance, all birds in North America. And so I would encourage all of you to download the Merlin app, which you can take a picture of a bird, and it will tell you what bird it is, assuming it's a North American bird, and then give you information about it. So now you actually can have expert level knowledge, expert level visual knowledge at your fingertips. Otherwise, you would have had to have a field guide with you, go talk to a birder expert. So this is, I think, a pretty cool application of it. A few other cool things. Sorry if I keep saying cool, but I really do think this is quite cool. Is Deep Dream. So you start with an input image, for instance, to animals for grazing, and you you put that through your network, and then you get the feature representation, and now you slightly modify it and optimize the image for that representation. So now you're just doing this kind of random walk in feature space, and then projecting that back down to the image using this optimization type of technique. And you get these really cool effects where now, you can think of Photoshop, you're manipulating individual pixels, but now you're really actually manipulating the image at an abstract level, and it's just some very beautiful stuff that comes out of it. And they call it Deep Dream because it's as though it's kind of having this dream of chaotically moving around in this feature space, and you get these just masterpieces that come out of it. I think it's very cool. Another thing, you may have already seen this, but has anyone heard of neural style transfer? A couple people have. So you start with two images. You have one image which is going to contain the content of the image you eventually want, and you have another image that's going to convey the style. So you want to take the style of the style image and then transfer that over to the content image and get out a new image that has both style and content. So this is a concrete example where you take Starry Night and this image here, and you take now the content of the right image with the style of the left image, and there's apps that can do this now. It's kind of like the new Instagram, in my mind at least. And yeah, it's just awesome what you can do with these things. And then another one that I think is just fantastic. You can so the color that things are is, again, just some pattern that you can learn. So you could, in theory, if you knew what was in an image, you could map a black and white image to color if you knew what this mapping was. And so what people have been able to do is actually train with black and white and color images, figure out what this mapping is based on content, and then apply it to old black and white photos, and then you can colorize them, get these really cool old-timey photos, but they look like they're not as, when you see a black and white photo, it kind of distances you from it because it's somehow not as real and tangible. But seeing these color photos is just quite amazing. So we talked a lot about, we talked only about discrimination, really. But there's also generation. We didn't even really mention this side of the equation at all, but people are starting to apply convolutional neural networks for generation as well. And so some of the early stuff with image generation, it does not look very good. I wouldn't say this looks great. But slowly it's been getting slightly better, and people have been working on CIFAR-10 primarily, trying to generate these 32 by 32 images. Eventually it'll move on to ImageNet. Some people are already working on trying to generate ImageNet photos. And you can do these kind of cool things where you're moving around in this latent space and generating the resulting output. So if you take, for instance, the representation of a man with glasses in this generative model, subtract man without glasses, so that should give you woman. Or no, that should give you the glasses, sorry. And then you add in the woman. My man and woman math is not very good, I'm sorry. But yeah, so you get glasses, and then you add in woman, and you get woman with glasses. So you can do these very interesting things, and it'll be really cool to see. Eventually, you can just, think of some thing that you'd like to see, and these networks will just be able to generate it, and it'll look just amazing. And then so you have these faces. Maybe from where you're sitting, they look fine, but there's some kind of ghoulish-looking people in here. So we're not quite there yet, but we're getting close. These are all generated by computers. So just to wrap up, we talked about convolutions, and why do we even use convolutions in the first place? Is because there was some invariances that we wanted to take advantage of. We had some priors on the data we were working with, and this same type of technique can be applied to one-dimensional data, three-dimensional data, anything you can really imagine that has these invariances along space or time. So you could think of, people apply convolutions to audio signals as well. They also apply convolutions to spatiotemporal data, where you have a series of frames that are progressing over time. And these convolutional neural networks have had just a profound impact on computer vision and a lot of other fields as well. And I want to highlight again what I talked about last time, which was that a lot of this was less to do with the models and more to do with the data and the hardware. It was only once the data and the hardware was there that people could really actually experiment with these models and develop better models. So there's still a lot of very interesting areas to explore. This is still a developing field. And there's also a lot of open problems, some of which I've highlighted here. But as we've kind of gone through these examples, it may have caught your eye that it's a little weird that we have to choose the network architecture. It seems like there should be a way in which we could learn it. We're not really doing any reasoning here, at least with the very basic convolutional neural networks. So maybe figuring out a way to make these models a little more capable. Making them able to learn from very few examples. So this is one thing neural networks are just notorious for, is that they need a lot of examples per class. So there's a lot of work being done on trying to fix this problem. And then really just understanding what they're doing, how they're learning, and getting a better sense and developing a more sound theory of how to train one of these things. So that's it.